The vastness of space, with its endless darkness and countless stars, planets, and celestial bodies, has always captivated humanity's curiosity. From the Earth's surface, this boundless universe may seem unreachable, but with the advancement of science and technology, it is slowly being explored. From the planets in our solar system to the Moon and Mars, these explorations have pushed the boundaries of human knowledge and taken significant strides towards understanding the mysteries of the universe. Leading these explorations are astronauts, the brave explorers of the modern age, who venture into the unknown realms of space. An astronaut is a person trained to explore space, conduct scientific research, and uncover the secrets of the cosmos. The word astronaut comes from the Greek words astron, meaning star, and nauts, meaning sailor, literally translating to star sailor. The first astronauts were at the forefront of the space race during the Cold War, but today they are professionals conducting scientific missions through international cooperation. In 1961, Yuri Gagarin made history as the first human in space, marking the beginning of the astronaut profession. Then, in 1969, Neil Armstrong's landing on the Moon became one of humanity's greatest achievements. Modern astronauts do more than just travel to space, they also conduct research in fields like biology, physics, and chemistry in microgravity environments. Astronauts who live in space, often on platforms like the International Space Station, spend extended periods working on critical tasks to ensure humanity's sustainable presence in space. As technology advances, astronauts are being meticulously trained for missions to distant planets like Mars. Today, their role extends beyond space exploration. They are also working to make human life possible on other planets, developing new technologies, and conducting scientific research to understand humanity's place in the universe. Life in space is vastly different from life on Earth, and the daily routines of astronauts are meticulously planned to accommodate the effects of a zero-gravity environment. In microgravity, body functions change, movement becomes difficult, and even simple tasks are challenging to perform. As a result, astronauts must adapt how they eat, sleep, and exercise to maintain their health and complete their missions successfully. Eating in space is far from the usual experience due to the lack of gravity. Food and liquids can float freely, so meals are specially packaged and consumed with care. Most food is either freeze-dried or pre-packaged and can be rehydrated by astronauts before consumption. The packaging is designed to prevent spills, and solid food can be eaten directly from the packs, while liquids are consumed through special straws. Nutrition is carefully monitored since the body loses mass in space, and muscles and bones can weaken. Astronauts must consume a specific balance of proteins, carbohydrates, vitamins, and minerals, and on long missions, their diet is regularly reviewed to ensure they stay healthy. Sleeping in a weightless environment can be an unusual experience at first, as the body floats freely in space. To address this, astronauts sleep in special sleeping pods within spacecraft or on the International Space Station. These pods help them stay secure and provide a controlled space for rest. These sleeping pods are equipped with straps that keep astronauts in a fixed position. To avoid floating or drifting while they sleep, astronauts secure themselves with these straps. Since there is no natural day and night cycle in space, maintaining a regular sleep schedule is essential. Astronauts must follow a set sleep routine to regulate their biological clocks and avoid fatigue. Typically, an 8-hour sleep schedule is followed, and astronauts use sleep masks and earplugs to ensure a quiet, dark environment for rest. Exercise in space is crucial for astronauts' health. In a microgravity environment, muscles and bones don't work against gravity like they do on Earth, causing them to weaken rapidly. To prevent muscle atrophy and bone density loss, astronauts exercise daily. The International Space Station is equipped with special exercise machines, including treadmills, stationary bikes, and resistance devices. On treadmills, astronauts strap themselves down to prevent floating while running, and stationary bikes help strengthen leg muscles. Although resistance machines don't use weights, they provide resistance that helps keep muscles active. Astronauts typically spend about 2 hours a day exercising, which helps maintain muscle mass, prevent bone loss, and support cardiovascular health. Exercise plays a vital role in ensuring that astronauts remain physically and mentally fit during their missions. Personal hygiene in space also requires special care. With water floating freely in space, its use is limited, so astronauts clean themselves with moist wipes and water-efficient soaps. For washing their hair, special no-rinse shampoos are used. All these activities are designed to make life in space sustainable. To stay healthy in microgravity, complete their missions successfully, and expand humanity's presence in space, astronauts must adhere to these routines. Becoming an astronaut requires great discipline, skill, and physical endurance. Astronauts take on critical roles during space missions, and they must possess both scientific and technical knowledge. Therefore, the selection and training of an astronaut is a rigorous and demanding process, covering everything from the application phase to technical skills, psychological resilience, and physical endurance. Candidates are required to hold at least a bachelor's degree in fields such as engineering, physics, biology, chemistry, mathematics, or computer science. Many astronaut candidates are scientists with master's or doctoral degrees. Additionally, candidates are typically expected to have 3 to 5 years of professional experience in space-related fields. This experience helps them handle the technical challenges they will face during space missions. Astronauts undergo a thorough medical examination, where cardiovascular health, eye function, and musculoskeletal health are assessed. They must also meet specific height and weight requirements. Given the harsh conditions of space, superior physical fitness is crucial. Long periods of isolation, working under pressure, and teamwork are key factors in astronaut missions. Therefore, candidates undergo psychological resilience tests. These tests evaluate how they respond to stressful conditions and assess their ability to work well within a team. After submitting their applications, candidates are put through a series of interviews and tests. Only the most qualified candidates pass this process and are selected to begin astronaut training. Those who successfully complete the selection process enter a long and intense training period. This training prepares astronauts both physically and mentally for the challenging missions ahead. Training covers several key areas. Astronaut candidates receive instruction in scientific and technical subjects such as space mechanics, orbital dynamics, spacecraft systems, and navigation. They also learn how to handle emergency situations in space and conduct scientific experiments during their missions. Candidates are trained through realistic simulations, where they practice spacecraft operations, working in microgravity, performing spacewalks, and carrying out International Space Station tasks. During this time, astronauts learn how to solve technical problems they might encounter on actual missions. To adapt to weightlessness, they also undergo training on special aircraft that perform parabolic flights, which simulate zero-gravity conditions. These planes ascend to a specific altitude and then suddenly dive, creating a few seconds of weightlessness. During these brief moments, astronauts experience moving and working in a zero-gravity environment. To prepare for spacewalks, they undergo underwater training, as water is the best medium to simulate the conditions of weightlessness. Wearing special diving suits, astronauts practice tasks such as exiting spacecraft and performing repairs underwater. This training enhances their body coordination and ability to work with spacesuits. Astronauts must maintain a high level of physical fitness. In space, the microgravity environment can cause muscles and bones to weaken quickly. For this reason, they undergo endurance and strength training. Additionally, astronauts learn to work under extreme conditions to preserve their resilience during emergencies. After completing basic training, astronaut candidates continue with advanced training until they are assigned to a mission. At this stage, they receive specific, detailed training related to their designated mission. For example, an astronaut heading to the International Space Station will learn its systems thoroughly, receive training on the scientific experiments they'll conduct, and prepare for emergency scenarios. Furthermore, astronauts must develop communication skills in multiple languages. Those working on the ISS are required to learn Russian, as Russia's Soyuz spacecraft is used for transport to the ISS. They also enhance their teamwork skills to ensure effective collaboration in international missions. Psychological preparation is equally crucial. Astronauts train to handle long-term isolation, stress, and uncertainty. During this process, they receive support from psychologists to manage group dynamics and personal stress in difficult conditions. They also learn to cope with challenges such as prolonged isolation, being away from family, and limited communication during a mission. A spacewalk is both a technically challenging and thrilling experience for astronauts. It involves stepping outside a spacecraft to perform repairs, maintenance, or conduct scientific experiments. Officially known as an extravehicular activity, spacewalks present significant risks but also the potential for great achievements. Each spacewalk requires thorough preparation. Astronauts must wear specially designed spacesuits to work outside a spacecraft or the International Space Station. These suits protect them from the vacuum of space, extreme temperature changes, micrometeoroids, and radiation. Additionally, the suit provides astronauts with oxygen, water, temperature regulation, and mobility. During a spacewalk, astronauts exit the spacecraft while secured with safety tethers to complete their tasks. These tasks often include repairing spacecraft, installing solar panels, or assembling scientific equipment. Before embarking on spacewalks, astronauts undergo extensive underwater training on Earth, as underwater movement closely simulates working in a weightless environment. Spacewalks come with numerous challenges. Working in microgravity itself is difficult, but external factors make spacewalks even more dangerous. For instance, in space, temperatures can reach 120 degrees Celsius in direct sunlight and drop to -150 degrees Celsius in shadow. Spacesuits are designed to shield astronauts from these extreme temperature fluctuations, but the conditions still make spacewalks incredibly demanding. Another risk is the presence of constantly moving particles and micrometeoroids in space. These objects can travel at thousands of kilometers per hour, and if they collide with an astronaut or spacecraft, they can cause serious damage. While spacesuits are built to withstand these threats, the risk is always present. Space is a vacuum, meaning there is no air pressure, so the pressure inside a spacesuit is vastly different from the vacuum outside. If a spacesuit were to develop a leak, the astronaut could face life-threatening consequences. This is why spacesuits are meticulously designed and rigorously tested. Additionally, spacesuits carry a limited supply of oxygen, restricting the duration of each spacewalk. Astronauts must complete their tasks within this time frame, adding another layer of complexity to the mission. Astronauts must complete their tasks within a set time frame, or they risk running out of oxygen. Moving inside a spacesuit is far more challenging than in Earth's gravity, as the thick, multi-layered suit requires astronauts to exert more muscle strength. Even though there is no gravity in space, installing or repairing large, heavy components requires significant physical effort, pushing their bodies to the limit. The first astronauts in history were pioneers who took revolutionary steps in humanity's journey into space. These brave individuals participated in groundbreaking missions, from the first spaceflights to the first steps on the moon. The first human to travel into space was Soviet cosmonaut Yuri Gagarin. On April 12, 1961, he successfully orbited Earth aboard the Vostok 1 spacecraft, completing a flight that lasted approximately 108 minutes. This mission marked a major Soviet victory in the space race. Gagarin's single orbit around Earth was a monumental milestone, making him a hero upon his return and earning him the title of the first human to gaze upon the heavens. The Vostok 1 mission ushered both the Soviet Union and the world into a new era of space exploration. Just weeks after Gagarin's flight, the United States made its own mark in space history. On May 5, 1961, Alan Shepard flew aboard the Freedom 7 spacecraft, performing a suborbital flight that did not reach orbit but still allowed him to experience weightlessness. The mission only lasted 15 minutes, but it was a major step for the US in the space race against the Soviets. Shepard later became the fifth person to walk on the moon during the Apollo 14 mission in 1971. American astronaut John Glenn made history on February 20, 1962, when he became the first American to orbit Earth during the Friendship 7 mission. As part of the Mercury program, Glenn circled the planet 3 times, spending nearly 5 hours in space. His flight was a significant achievement for the US in the space race against the Soviet Union. Years later, in 1998, Glenn returned to space at the age of 77, becoming the oldest astronaut to fly into space. One of the most important moments in world history occurred on July 20, 1969, when Neil Armstrong took his first step on the moon, marking a defining achievement in human space exploration. The Apollo 11 mission marked humanity's first successful landing on the moon. Alongside Neil Armstrong were his fellow astronauts, Buzz Aldrin and Michael Collins. Aldrin followed Armstrong, becoming the second person to set foot on the moon. This historic mission ensured the U.S. victory in the space race and is regarded as one of the greatest achievements in human history. Soviet cosmonaut Alexei Leonov was the first person to perform a spacewalk. On March 18, 1965, during the Voskhod 2 mission, he exited the spacecraft and floated freely in space for about 12 minutes. Leonov's spacewalk was a significant technical achievement, but it also revealed the dangers of extravehicular activity. His suit expanded, making it difficult for him to return to the spacecraft. However, Leonov remained calm and managed to safely re-enter the capsule, demonstrating the risks involved in space exploration. The International Space Station is one of the largest international collaborations dedicated to space exploration, bringing together astronauts and scientists from all over the world. Launched in 1998, the ISS was built through a partnership between NASA, Roscosmos, the European Space Agency, Japan, and the Canadian Space Agency. Astronauts aboard the ISS conduct numerous scientific experiments and research while orbiting Earth. The work done on the station is particularly valuable for understanding the effects of long-term space travel on the human body. While conducting experiments in a microgravity environment, astronauts contribute to groundbreaking discoveries in fields such as medicine, biology, physics, materials science, and climate research. Moreover, the ISS has become a symbol of peace, as it fosters collaboration among astronauts from different nations, breaking cultural boundaries. Some of the most important studies carried out on the ISS focus on growing plants in space, analyzing the effects of radiation on the human body, and examining bone and muscle loss in extreme conditions. These findings are critical for preparing future human missions to distant destinations like Mars. Additionally, the technologies developed on the ISS are being applied across various fields on Earth, from healthcare to the energy sector. Manned missions to Mars and beyond are considered one of the greatest goals in the history of space exploration. Today's astronauts, through their experiences on the International Space Station, are laying the groundwork for the knowledge and technology needed for future Mars missions, while the next generation of astronauts is preparing for this challenging endeavor. A journey to Mars is far more complex and risky than any mission conducted to date. Astronauts will spend months traveling in space, land on Mars, and live and work on its surface. This mission presents significant physical and psychological challenges. NASA, SpaceX, ESA, and other space agencies are working intensively to develop the infrastructure and technology required to send humans to Mars. For such missions, astronauts must endure extended space travel, work in a zero-gravity environment, and be protected from radiation. Moreover, life support systems on Mars, energy production, and sustainable food production are critical factors for the success of these missions. These missions are seen as the beginning of a new era for humanity, with astronauts on the path to becoming pioneers of a new chapter on Mars. Future astronauts are receiving both scientific and technological training in preparation for this deep space journey, ensuring humanity is ready to embark on this extraordinary voyage. NASA's Artemis program and SpaceX's Starship projects stand out as major milestones toward this goal. These missions not only aim to reach Mars but could also open the door to exploring more distant regions of the solar system. Today, we're delving into a groundbreaking achievement in space agriculture. Astronaut Shane Kimbrough recently conducted a remarkable experiment aboard the International Space Station, where he harvested lettuce grown in space. This may seem like a small task, but it's actually a significant milestone. Growing food in space is crucial for long-term missions, especially those extending to Mars or the Moon. Currently, astronauts rely on pre-packaged foods, which are not ideal for extended space missions. The ability to grow fresh produce like lettuce in space has profound implications. Not only does it provide astronauts with fresh, nutritious food, but it also reduces the need for constant resupply missions from Earth, which are costly and complex. Shane Kimbrough's lettuce harvest is more than just a novel experiment, it represents a step towards sustainable space travel. By cultivating plants in microgravity, scientists are learning how to manage growth conditions and improve space farming techniques. These advancements in space agriculture could pave the way for future space farms that will support human colonies on other planets. The success of growing lettuce in the ISS is just the beginning of a new era in space exploration and sustainability. Let's dive deeper into the technical aspects of growing plants in space. One of the major challenges is the microgravity environment aboard the ISS. Unlike on Earth, where gravity helps roots grow downward and stems upward, plants in space need to adapt to this zero-gravity condition. To overcome this, scientists use specialized growing systems. For instance, on the ISS, plants are grown in hydroponic systems, which use nutrient-rich water instead of soil. This method ensures that plants receive all the essential nutrients they need, even in the absence of gravity. Another key technology is the use of LED lighting. Since natural sunlight is not available in space, astronauts rely on artificial lighting to mimic the sun's spectrum. These LED lights are precisely controlled to provide the right amount of light for each stage of plant growth. These advancements in space farming not only support astronaut health but also offer valuable insights into how plants grow under different conditions. Understanding these processes helps scientists develop better methods for growing food in space and can even improve agricultural practices on Earth. Furthermore, space farming technologies have practical applications beyond space missions. They can be adapted for use in extreme environments on Earth, such as arid regions or urban areas where space is limited. The innovations developed for space agriculture could revolutionize how we grow food on our own planet. Looking ahead, the future of space agriculture is both exciting and promising. Researchers are exploring the cultivation of a variety of crops beyond lettuce, including vegetables, fruits, and grains. The goal is to create self-sustaining food systems that can support long-term missions to distant planets. One innovative approach is the development of closed-loop systems, where waste products from one process are used to support another. For example, plant waste can be converted into nutrients for new plants or even used to produce oxygen, creating a more sustainable environment for astronauts. Another key area of research is improving plant growth in microgravity. Scientists are developing new growth mediums and nutrient delivery systems to optimize plant health and yield. This research will be crucial for establishing larger-scale farms on Mars or the Moon. These advancements in space farming are not only for space missions. The technologies and methods developed for growing plants in space have potential applications on Earth as well. They can enhance urban agriculture, improve food security in arid regions, and contribute to more sustainable farming practices. Ultimately, the success of space agriculture could transform both space exploration and our approach to food production on Earth. By overcoming the challenges of growing food in space, we are laying the groundwork for a future where space travel and sustainable agriculture go hand in hand. Beyond the technical aspects, space farming has significant implications for astronaut health. Fresh produce provides essential vitamins and minerals that are often lacking in prepackaged space food. Having access to fresh, nutritious food can help maintain the astronauts' physical health and well-being during long missions. Psychologically, growing and consuming fresh food in space can have a positive impact on astronauts' mental health. The act of gardening and eating fresh food helps reduce stress and improve morale, which is crucial for maintaining mental health in the isolated and confined environment of space. Scientific research on space agriculture also contributes to our understanding of plant biology. Studying how plants adapt to microgravity provides valuable insights into their growth mechanisms and stress responses. This knowledge helps scientists develop better cultivation techniques both for space missions and Earth-based applications. Furthermore, the technologies developed for space farming can be applied to improve agricultural practices on Earth. For instance, the advancements in hydroponics and aeroponics can be used to enhance food production in urban areas, optimize water use, and support sustainable farming practices. Overall, space agriculture represents a convergence of science, technology, and human well-being. The progress made in this field not only supports future space exploration but also has the potential to revolutionize how we grow and consume food on our planet. As we advance in our space farming efforts, we pave the way for a more sustainable and healthy future both in space and on Earth. As we look to the future, space farming is expected to play a crucial role in enabling deep space exploration and habitation. Future missions to Mars or the Moon will rely on advanced agricultural systems to provide astronauts with a continuous supply of fresh food. This will be essential for long-duration missions and establishing permanent outposts. Several space agencies and private companies are already working on ambitious projects to expand space farming capabilities. For example, NASA's Veggie experiment aims to grow a variety of crops in space, while private ventures like the Red House are exploring new techniques to enhance plant growth and sustainability. International collaboration is also key to advancing space agriculture. Different space agencies around the world are sharing their research and technologies to accelerate progress. This cooperative approach not only enhances our collective understanding but also helps to develop standardized practices for space farming. Additionally, the lessons learned from space farming are fostering innovation in terrestrial agriculture. Techniques developed for space, such as efficient water use and nutrient delivery systems, are being adapted to address challenges like climate change and food security on Earth. In conclusion, space agriculture is not just about growing food in orbit, it's about paving the way for future space exploration and improving life on Earth. By overcoming the challenges of cultivating plants in space, we are not only advancing our space missions but also contributing to a more sustainable and resilient food system globally. To successfully cultivate potatoes on Mars, the establishment of specialized greenhouses or growth chambers is essential. These structures must be designed to create a controlled environment that can simulate Earth's conditions, including temperature, humidity, and atmospheric pressure. The greenhouses should be constructed using durable, lightweight materials capable of withstanding Mars' harsh conditions. Transparent or semi-transparent materials, such as polycarbonate or specialized Martian glass, will be necessary to allow for artificial light to penetrate while providing insulation against the extreme cold. A robust life support system is crucial for maintaining the greenhouse environment. This system would include air filtration and recycling units to ensure a continuous supply of oxygen and removal of carbon dioxide. Given the thin Martian atmosphere, which is composed mainly of carbon dioxide, a CO2 scrubber would help to maintain an optimal concentration of carbon dioxide for plant growth. Additionally, heating systems will need to be installed to maintain the temperature within the ideal range for potato cultivation, which is typically between 15 to 20 degrees Celsius. The Martian regolith, or soil, lacks the necessary nutrients for plant growth and must be supplemented with a suitable growth medium. A combination of hydroponic systems and enriched soil or artificial substrates would be used. For hydroponic systems, a nutrient solution rich in essential minerals and vitamins would be delivered directly to the plant roots. In conjunction with this, Martian soil could be processed to improve its fertility, incorporating organic matter and nutrients either brought from Earth or generated on-site through biological processes. Due to Mars' distance from the Sun, natural light is limited and significantly weaker compared to Earth. Therefore, artificial lighting systems, such as LED grow lights, will be necessary to supplement the light required for photosynthesis. These lights should be designed to mimic the full spectrum of sunlight to promote healthy plant growth. The lighting system would need to be energy efficient and capable of providing a consistent light cycle to simulate day and night conditions. Water is a critical resource for growing potatoes. On Mars, water can be extracted from the polar ice caps or subsurface reservoirs, but it will require purification and processing before use. A closed-loop water recycling system would be essential to minimize waste and ensure a continuous supply of clean water. This system would filter and recycle water from plant irrigation and condensation within the greenhouse environment. Mars lacks a magnetic field and thick atmosphere, which means that the surface is exposed to higher levels of cosmic radiation compared to Earth. The greenhouse structures must be designed to provide adequate shielding against this radiation to protect both the plants and any potential human occupants. This could involve incorporating radiation-resistant materials into the greenhouse construction and possibly using additional shielding techniques, such as regolith covering or water-based barriers. Ensuring that potatoes receive all the necessary nutrients for optimal growth can be challenging. On Mars, nutrient management will require careful monitoring and adjustment of the growth medium. Regular analysis of the soil or hydroponic solution will be necessary to maintain proper nutrient levels and prevent deficiencies or toxicities. Growing food on Mars has implications beyond just agriculture. The ability to produce fresh food can have a significant psychological impact on astronauts, contributing to their overall well-being and morale. Ensuring that the growing process is efficient and yields high-quality produce will be crucial for maintaining crew motivation and mental health during extended missions. Choosing the right potato varieties for Martian cultivation is crucial. Varieties that are resilient to stress and adaptable to varying conditions should be prioritized. Research into genetically modified or specially bred potato strains that can tolerate low light, limited water, and nutrient-poor conditions could enhance the likelihood of successful growth on Mars. Additionally, dwarf or compact potato varieties may be preferable due to space constraints within the greenhouse. Potatoes can be grown from seed potatoes, which are tubers cut into pieces with at least one eye per piece. In Martian greenhouses, planting can be carried out using hydroponic systems or in soil-less growth media. In hydroponic systems, seed potatoes would be placed in a nutrient-rich solution, while in soil-based systems, they would be planted in specially prepared Martian soil or artificial substrates. Automated planting systems may be employed to ensure precise placement and to reduce labor requirements. Continuous monitoring of environmental conditions within the greenhouse is essential to ensure optimal growth. This includes tracking temperature, humidity, light intensity, and CO2 levels. Advanced sensors and automated control systems will regulate these parameters and adjust as needed to maintain the ideal conditions for potato growth. Regular inspection of plant health will also be necessary to identify and address any issues, such as nutrient deficiencies, diseases, or pests. Potatoes typically take several months to grow and reach maturity. On Mars, the growing period may be slightly extended due to the controlled environment's specific conditions. Harvesting would involve careful extraction of the tubers from the growth medium, ensuring minimal damage to both the plants and the potatoes. Automated harvesting systems could be developed to handle the tubers efficiently and to streamline the process. The energy requirements for maintaining the greenhouse, including lighting, heating, and life support systems, will be substantial. Solar panels, potentially augmented by nuclear power sources, could provide a reliable and sustainable energy supply. The energy system should be designed to be robust and capable of handling the demands of the greenhouse operations while considering the limited solar energy available on Mars. Managing waste generated from plant cultivation is a critical aspect of sustaining a Martian agricultural system. Organic waste from potato plants can be composted or converted into useful byproducts, such as biochar or fertilizer, to enrich the growth medium. Additionally, waste management systems should be integrated to handle non-organic waste and ensure the overall efficiency of the greenhouse operations. A key aspect of long-term success in Martian agriculture is the recycling and sustainability of resources. Closed-loop systems that recycle water, nutrients, and organic matter will be essential for minimizing resource input and maximizing efficiency. Innovations in waste-to-resource technologies and recycling processes will contribute to the sustainability of the agricultural system. Once the initial potato cultivation system proves successful, scaling up operations to support a larger number of astronauts or a more extensive Martian colony will be necessary. This may involve expanding the number of greenhouses, optimizing resource use, and developing more advanced agricultural technologies. Collaboration with research institutions and private companies could drive further advancements and efficiencies. Continuous research and development will be crucial for improving Martian agriculture. This includes exploring new plant varieties, optimizing growth conditions, and developing more efficient technologies. Partnerships with Earth-based agricultural research organizations and space agencies will facilitate the sharing of knowledge and resources. The technologies and methods developed for growing potatoes on Mars have potential applications beyond space missions. Innovations in controlled environment agriculture could be applied to address challenges on Earth, such as urban farming, food security in arid regions, and sustainable agricultural practices. The lessons learned from Martian agriculture could drive advancements in how we produce food in challenging environments on our own planet. Integrating potato cultivation systems into Martian habitats requires careful planning to ensure seamless operation alongside other life support systems. The greenhouses or growth chambers will need to be connected to the habitat's overall infrastructure, including power, water, and waste management systems. Efficient layout and modular design will enable easy maintenance and expansion as the colony grows. The integration will also involve ensuring that the greenhouse structures are resilient to Martian environmental conditions, such as dust storms and temperature fluctuations. The ability to grow potatoes and other crops on Mars has profound implications for human settlement and long-term habitation. Fresh produce will enhance the nutritional quality of astronaut diets, reduce dependency on pre-packaged food supplies, and improve overall well-being. This self-sufficiency is critical for establishing a sustainable and resilient Martian colony. Additionally, successful agricultural systems will support psychological health by providing astronauts with a sense of accomplishment and connection to Earth-like activities, such as gardening. Looking ahead, the success of growing potatoes on Mars could pave the way for the cultivation of a wider variety of crops, supporting more extensive agricultural systems and larger colonies. Future missions may focus on improving crop yields, developing new growing techniques, and exploring the potential for growing other staple foods. The advancements made in Martian agriculture will also contribute to our understanding of sustainable practices that can be applied both on Mars and Earth, fostering innovations in space exploration and terrestrial agriculture alike.